Hello everyone, I'm Kiran Rokade. I'm going to talk about Graphon games with multiple Equilibria. This is a joint work with my advisor, Professor Francesca Parise from Cornell University. So why are we talking about Graphon games? Graphon games are tools to study network games. And what are network games? Let me give you some examples. Imagine a scenario where you're trying to elect a political candidate based on public opinion. Or say you are a seller trying to price your good based on the prices of similar goods in a competitive market. Or suppose you're trying to decide whether to buy a product or not based on influence of your friends on social media. All these scenarios constitute a network game. So essentially, in a network game, players are part of a network, and the decisions that the players make depend on their neighbors in the network. So let me give you a mathematical model of a network game. So a network game consists of a network that is represented by an adjacency matrix. The adjacency matrix is a 0-1 matrix where a 1 in position ij means that players I and j are connected, whereas 0 means that players I and j are not connected. The game consists of a utility function u, which takes 3 arguments. The first argument is the strategy of the player. The second argument is the local aggregate, which consists of the strategies of all the other players. So this is essentially an average of the strategies of all the neighbors of player I in the network. And the third argument of the utility function is the heterogeneity parameter. This parameter distinguishes player I from other players in the network. Now we can define the notion of an equilibrium in a network game called a network equilibrium. We say that a vector S is a network equilibrium if no player I can benefit by unilaterally deviating to an alternate strategy S tilde I. Now let me give you an example of a network game. On the right, I have a network game of 3 players where players are allowed to choose between 2 strategies, -1 and +1. And the utility function of the game is designed in such a way that players are incentivized to choose a strategy S that is as close as possible to their local aggregate Z. So in this game, you can verify that if all the players play the strategy +1, then that is a network equilibrium. But what happens if player 1 decides to deviate to the strategy -1? Then the local aggregate of player 1 is 2/3, and -1 is not as close to 2/3 as +1. So this is not a network equilibrium. One issue with network games is that networks can be very hard to deal with. For example, if you imagine a game that is played by users that are part of Facebook, then the network will consist of more than 2 billion nodes. And hence, computing, say, an equilibrium of the network game can be computationally intractable. Some other challenges in network games are that some parts of the network may be unknown, or the network may be changing with time. Now, these issues are common in the literature of networks, and people have made an observation which says that in such cases, a probabilistic model of a network can be useful to infer properties of the network. Now, using this observation, we adopt graphons as a general probabilistic model of network games. So in this talk, we are interested in answering 2 questions. The first question is, what is a probabilistic model of a network game? And the answer to that is going to be a Graphon game, which we will see shortly. The second question that we are interested in is that how are Graphon games related to network games? So what is a Graphon game? A Graphon game consists of a continuum of players denoted by the interval 0, 1. And just like an adjacency matrix, here you have a Graphon, which is a function on the unit square. You can interpret a Graphon as a function which denotes the strength of the connection between players. Now, in a Graphon game, just like a network game, you have a utility function that takes 3 arguments. The first argument is the strategy of player X. The second argument is the local aggregate of player X, which is the integral of the strategies of the neighbors of player X in the Graphon. And the third argument is the heterogeneity parameter, which distinguishes player X from other players in the network. Now, similar to a network equilibrium, you can define the notion of an equilibrium in a Graphon game. This is called a Graphon equilibrium. So we say that a function S is a Graphon equilibrium if no player X can change his strategy from Sx to S tilde X and increase his utility. So on the right, I have an example of a Graphon. So this Graphon divides the players into 2 communities. The first community is the subinterval 0 to 0.5, and the second community is the subinterval 0.5 to 1. Now, as you can see in the Graphon, the players from the first community are connected to all the players from the second community and vice versa. So now that we know what are Graphon games and what are network games, the next question that we are interested in is how are these two related? So it is known in the literature that a Graphon is a probabilistic model to sample finite networks. Now, how do we do this sampling? The sampling procedure goes as follows. You first sample n points, t1 up to tn, from the interval 0, 1, uniformly at random. Then you assign entries to the adjacency matrix as follows. You say that the ijth entry of the adjacency matrix is 1 with probability w of tij. Otherwise, it is 0. Now we can extend this procedure to sampling a network game from a Graphon game. How do we do that? We first sample the strategy sets of all the players from the strategy set correspondence. Then we sample the heterogeneity parameters of all the players from the heterogeneity function. So in this way, if you are given a Graphon game, you can sample n points from the unit interval and get a network game of n players. So let me give you an example of this sampling procedure. Suppose I have a Graphon game which is denoted using the objects at the top. So you have a Graphon, a strategy set correspondence, and a heterogeneity function. Let's say I want to sample a network game of 3 players. So I sample 3 points, t1, t2, and t3, uniformly at random from the unit interval. And let's say these points are 0.1, 0.3, and 0.7. Now to sample an adjacency matrix, I look at the corresponding entries in the Graphon and sample a random variable from it. For example, if you look at the entry at position 1, 2, then we look at the value of the Graphon at t1, t2, which is in this case 0.1. So the corresponding entry would be 1 with probability 0.1. Otherwise, it will be 0. In this instance, it happens to be 0. And likewise, you can sample a strategy set for every player and a heterogeneity parameter for every player. So now that we know how to sample a network game from a Graphon game, we can relate the equilibria of these two games. And this is the topic of our first result. So suppose you are given a Graphon game and say you sample n points uniformly at random from the unit interval. Then you get a network game of n players using the procedure we just saw. And let's say S is a function which is an equilibrium of the Graphon game. Then from S, you can obtain a strategy for the network game as follows. For every player I in the network game, you assign the strategy S of Ti. Now the result says that the strategy vector Sn obtained this way is an epsilon network equilibrium of the network game with high probability. So what is an epsilon network equilibrium? It is nothing but a network equilibrium where you allow an epsilon error in the strategy profile. So to summarize this result in one line, you can say that every Graphon equilibrium yields an approximate network equilibrium if the number of players is large enough. So now that we know what are Graphon games and how Graphon games are related to network games, the last question that we are interested in is how to compute a Graphon equilibrium. So to answer this question, we first make an observation about networks in general. So it is observed in the literature that most networks that are observed in practice happen to have a low rank. And there is some theoretical justification behind this fact as well. So based on this observation, we make an assumption on our Graphon. We assume that our Graphon has a finite rank R. How do we define the rank of a Graphon? It's similar to the definition of the rank of a matrix. If we do an eigenvalue decomposition of our Graphon and say the Graphon has R non-zero eigenvalues, then we say that the rank of the Graphon is R. We also assume that our utility function has a special structure, and this structure is such that the local aggregate appears in the utility function as a polynomial, and we assume that the degree of this polynomial is P. So with these assumptions, our second result says that the equilibria of a Graphon game can be computed by solving a system of polynomial equations which has R unknowns, and each equation has a total degree P. So this is an R dimensional problem, and R is generally very small compared to the number of players in a network game. For example, in Facebook, as we saw, we have more than 2 billion nodes. But the rank of a network is typically very small, like 5 or 10, and so on. So let me give you some intuition behind why this result is true. So if you observe carefully, the local aggregate is a map of the strategy profile through the Graphon. It's a linear map. Now, if the Graphon has rank R, then this local aggregate lives in an R-dimensional subspace. So computing a Graphon equilibrium essentially boils down to computing the R unknown components of the local aggregate. And that's why this becomes an R-dimensional problem. So to summarize, Graphon games are probabilistic models of network games, and the equilibria of Graphon games and network games are closely related. If the Graphon has a low rank structure, which is observed in practice, then the equilibria of Graphon games can be computed efficiently. You can find more results and details about these results on our paper online. We have some interesting points for future work. The first interesting question is that how we can estimate a Graphon given a network. The second interesting question would be how to design a Graphon game so that you can control the outcome of a corresponding network game. Now, with this, I would like to end my talk. Thank you for your attention.